How does P gain affect PID control? Imagine you're trying to keep a boat steady in choppy waters. The way you turn the wheel depends on how much you feel the boat is drifting. That feeling is similar to what proportional gain does in a PID controller. It measures how strongly the system reacts to current errors or how far off the process variable is from the set point. When you increase the proportional gain, the controller responds more aggressively to errors, making the system correct itself faster. Think of it like turning the steering wheel more sharply when the boat starts to drift. But there's a catch. If the proportional gain gets too high, the system can start to overreact. Instead of smoothly correcting, it might overshoot the target and then swing back, causing oscillations. This is like steering too hard and making the boat wobble side to side. That instability can make the system unreliable or even damage mechanical parts over time. On the other hand, if the proportional gain is too low, the response becomes sluggish. The system reacts slowly to errors, taking longer to reach the desired set point, which might not be acceptable in precise control situations. In practice, tuning the proportional gain involves starting with a low value and gradually increasing it until the system begins to oscillate. That point shows the maximum gain before instability. Then, you back off a little to find a sweet spot where the system responds quickly but remains stable. Remember, the proportional gain alone cannot fix steady-state errors, which are small persistent differences that stay after the system settles. To eliminate those, you need the integral part of the controller, which sums up past errors over time. The derivative part then helps predict future errors, smoothing out the response and preventing overshoot. In mechanical systems like controlling temperature, pressure, or position, the P gain plays a vital role. For example, when controlling a valve to keep fluid levels steady, the P gain determines how much the valve opens or closes based on the current level error. If set right, the system reacts swiftly without causing oscillations or mechanical wear. Too high, and you risk instability. Too low, and the system feels sluggish. So, in essence, P gain is about balancing speed and stability. It sets how strongly the controller reacts to errors, shaping the overall behavior of the system. Properly tuning this parameter is key to achieving smooth, reliable control in many engineering applications.